Okay, we will talk about Wagner Nelson method right now, which is the other method in which we will determine Ka using it. This is the second method that we know. The first method was the residual method, right? We the one that we talked about in earlier recordings. So we will talk about the Wagner Nelson method, how we determine Ka using Wagner Nelson method, and this method is in your slide starting from slide 41. Okay, so the idea or the concept of Wagner Nelson method that I need to determine the percentage of unabsorbed drug, okay, or fraction of unabsorbed drug, either this or this, doesn't matter, and I need to determine it to be able to draw it in a profile as a fraction or as a percentage per time. Okay, so this is the idea of the whole method. I need to determine either the fraction or the percentage of unabsorbed or fraction or percentage unabsorbed of the drug. Okay, how we will do that, I will go into details of the concept, how we reach this point, or how we will reach this point to be able to determine percentage of unabsorbed drug. So let's start from the beginning of our model. We have this, we have this, we have this, and we have dose, XGI, if we are talking about oral, amount in the body, amount eliminated, right? So the dose that is administered at any certain or determined time will be equal the sum of all the amounts that we have at different places as a mass balance equation, right? Similar to whatever we did before in the profiles that we have many amounts. Remember the profiles that we have different amounts, either amount in the body or cumulative amount versus time, as amount in the body, cumulative amount eliminated, and amount in the GI. This is the whole thing. At any taken time point, the dose will be the sum of all the amounts as mass balance. It will be XGI at certain time plus XP at certain time plus amount eliminated at certain time. Again, this is the absorbable or to be absorbed. This is the amount in the body, and this is the amount eliminated. If we are talking about the amount absorbed of the drug, then anything that past this point is absorbed, right? Either is absorbed and is still in the body or absorbed and eliminated. So it will be equal the amount in the body plus the amount and the elimination side. Okay, this is the amount absorbed at certain time, right? If we want to determine the fraction of the drug or the amount of the drug absorbed, this will be the amount absorbed at certain time over the amount absorbed total, which is at time infinity, right? And to determine the fraction of unabsorbed will be 1 minus the fraction absorbed, and it will be equal to 1 minus amount absorbed at certain time over amount absorbed at time infinity, right? So let's go here. This is the key to determine this, and if I can determine this, I can determine this by default, right? So let's continue and see what we will have. 18, and let's go. If we have the dose, the amount absorbed at certain time, which is equal the amount in the body plus the amount eliminated, I know that this equal concentration multiplied to volume distribution. As I know, concentration at certain time equal the amount in the body at certain time, right? Over VD. So the amount will be concentration multiplied to VD, right? This is one thing. Another thing, I know from whatever we know from the total clearance, if you remember, right? It will be equal the amount eliminated cumulative certain time according to the time that we have here. So if it's 0 to infinity, then this will be 0 to infinity. 0 to certain time will be 0 to certain time, right? So I will have here, if it's until eliminated per unit of time, until certain time, it will be equal to total clearance, which is K VD, multiplied to area under the curve from 0 until certain time, right? So this will be amount absorbed at certain time. Again, back to here. This is the one that I just wrote, okay? So amount, concentration versus multiplied to VD to determine the amount in the body, and amount eliminated by using this, okay? If I want, this is at time t. If I wanted at time infinity, what will be different? First of all, if we are talking about this CB versus time, at time equal infinity, the concentration will be equal to what? 0. So I will lose the whole thing, right? This is at time equal infinity. Plus K will be the same, VD will be the same, and area under the curve will be rather 0 to certain time, 0 to infinity, right? If total 0 to infinity, if I'm talking about the total amount eliminated. So according to this, I finished this. So I can determine the fraction of the drug absorbed, right? Which will be equal, according to this, amount absorbed certain time over amount absorbed at time infinity, which will be equal CB at certain time, VD, K, VD, area under the curve 0 to certain time, over K, VD, area under the curve 0 to infinity, right? We notice that we have what? So it will be equal CB at certain time plus K, area under the curve from 0 to time, over K multiplied to area under the curve from 0 to infinity, right? If I want to determine, this is the fraction absorbed. If I want to determine the fraction unabsorbed, it will be 1 minus CB at certain time, K, right? The whole fraction absorbed. Area under the curve from 0 to infinity over K, area under the curve from 0 to certain time, 0 to infinity. Okay? This is what mathematically we can determine the fraction unabsorbed. Okay? And if you see whatever that we have in the equation of either this or this, we can have all the terms. At certain time, I have concentration that is measured at certain time, whatever the time that I have. You can determine area under the curve from 0 until certain time, right? And we were able to do this by using concentration versus time, right? On a rectilinear to do what? Trapezoidal method. But when we are talking 0 until certain time, which means that it will be from 0 until that time, cumulative, which is the sum of all of them until that time. When we are talking about area under the curve from 0 to infinity, it will be our last one here, area under the curve from t last, as we already know. Area under the curve from 0 to infinity will be equal to area under the curve from 0 to last plus area under the curve from last to infinity, as we already know how to determine it. Trapezoids versus integration. And how we determine this? From the linear regression, slope of the linear regression of what? Of the terminal phase. If we are talking about the common case that we have, and we are not talking about flip-flop. Okay, so mathematically or experimentally, I can determine all the terms in this. Let's stop here and go back in one of the concepts that we talked about earlier. Okay, remember when we were talking about xgi at certain time? Let's just make sure that, yes, I'm covering it with the cam. And this equal f x node, which is xgi node, if you remember, multiplied to the e minus ka time. You remember this, right? Which is the same as xgi at certain time equal xgi node e minus ka multiplied to the time. It's the same. Okay, and when we wanted to either to have it as xgi at certain time or log xgi or ln lgi on a semilog, let's say semilog, we add all the, you should be able to have all of them, right? And I think I wrote this already, but it's fine. xgi at certain time, xgi at certain time, xgi log certain time, and len xgi at certain time. We said that according to this, it will be on rectilinear exponential. This will be on a semilog linear, or seems to be linear, and we will have this and we will have this. So this is the profile that we have. If we go back to the definition of this, it was the absorbable amount, or the amount to be absorbed, what remained to be absorbed. Or in other terms, it's not absorbed yet, right? It's everything other than what is absorbed. So if we take this as a fraction from this, which means if I have xgi at certain time, that is equal fx node e ka multiplied to the time. If I just divide on this, I just divide on this, okay, it will be what? Fraction of the drug unabsorbed, right? Because whatever that you have at certain time from the total, or the initial that you have from that time. So I can have the idea from this, because we were using this to determine what? If you remember, Ka, right? But we had a problem that experimentally I can determine this. But now, as you know, this is the fraction unabsorbed, which is already, you know, that it's 1 minus absorbed amount over absorbed amount at certain time over amount absorbed at time infinity. If I can determine this mathematically, as we just say, or see, as in here, okay, we can determine it. And I know from this that I can determine the absorption rate constant. So it means that rather than having this, I'll draw it here, you can have it whatever the, is it fraction unabsorbed, percentage unabsorbed, or fraction unabsorbed, okay? Still we are in the, okay, I will have it here, here, and here, okay? So we will have, I will use fraction, but it's the same for the percentage, fraction unabsorbed. It's the same as here, but you are dividing the whole thing on the XGI node, right? Fraction unabsorbed, fraction unabsorbed, but in a log term and in a len term of the fraction unabsorbed. Okay, and here we are talking about rectilinear, semilog, rectilinear, rectilinear. We will have it as exponential, we will have it seems as linear, we will have it linear, and we will have it as linear. Okay, and we can determine from the slope, as you know, if it's log, right? Sorry, Ka and Ka from here. And here, either it will be exponential equation, or as we already know, you need to transform the data that you have to get it right. Okay, and this is true either if you have it as a percentage or as a fraction. So we can know using, or we reach the point using Wagner Nelson method that I determine Ka, which is absorption rate constant, in which I can determine half-life of absorption of the drug from just knowing some kind of information such as area under the curve and K and measured concentration at certain time. Okay, this is the second way to determine Ka. Before we go into other subject, I need to have some comments or notes about Wagner Nelson method. First of all, when we are using Wagner Nelson method, it doesn't matter if I have that difference between Ka and K as we have in the residual method, because I'm just determining Ka, so it doesn't matter if they are near each other or not. So the 5-fold is not a rule to determine it, so it's accurate whatsoever. Okay, and another thing with time, for sure this is with time versus time, and it's here also versus time. Sorry, I missed this. Okay, with time, as we are talking about the absorption will reach the maximum with time. Okay, so the terminal part or terminal phase that we have usually deviates from linearity. Okay, and it's difficult to have it accurately. So usually we don't use the terminal phase to determine the slope that we have or the slope that we want. And you can see this some kind of deviation on your slide number 47. Okay, at its semilog, this is what you have in your slide 47. So it's a semilog profile, and we have some deviation here. So we don't use the terminal phase. That's why we usually, what we do, we use the initial phase and the fraction unabsorbed versus time in all the profiles to determine the slope. Okay, so we don't use the terminal phase, we use the initial phase in the profile. And that's because once I reach the total absorption, I start to have nonlinear behavior at the end because it's not accurate to determine it. Okay, which is again different than whatever that we said before about the K determination from the terminal phase, right? As we said, the absorption and elimination rate constant is going to be near each other. We need to determine K again, and the required calculation and the overall thing compared to the residual, as we saw here, is a little bit more in need of calculation, which is considered as disadvantage. Another thing, it's not like residual, you need to have a linear kinetic to use it. It's true that we will not have linear profile here unless we have linear kinetic and linear constant, right? It's a first order constant, but we can use it either it's first order or other orders. But to have it as linear in those profile, it will be first order kinetic. Okay, so by this, it will be the end of Wagner Nelson, and it will be the end of recording number 8. Okay, see you in the other one.